Hello everyone, we are going to present our system for declarative querying of real-time video streams involving objects and their interactions. The aim of this project is to make object interactions, such as human throwing a baseball, first-class citizens to query processing. Such a functionality unlocks a lot of expressive querying power in real-time video streams. We can observe two images containing specific actions. On the left we can see an athlete playing tennis, and on the right an athlete playing football. Deep neural nets have enabled sophisticated information extraction out of images. However, there are still many limitations in applying deep neural models at scale in the real world since it is computationally expensive at scale. In our previous work we proposed techniques to speed up declarative queries that involve objects of specific types on video frames with associated spatial relationships among them. Here we extend the work to capture object interactions. In this work, we are going to focus on efficiently capturing interactions among query objects. For example, as shown in the left picture, in a tennis match, we want to find out the frames when the player hits the ball, which is an interaction type between the player and the tennis ball. Also, as shown in the right picture, we got frames where a player interacts with the football. Since our framework enables us to query object interactions, much more interesting queries become possible, such as detecting frames in which a human holds a gun or a human breaking a window. For the interaction of the left picture, the corresponding query in SQL is shown on the right, where two classifiers, C1 and C2, are employed to detect the human and tennis ball. Using features F1 and F2, extracted from the frame and checking whether the objects are related via a kicking interaction. Here we show the overall structure of the system. With the arrival of frames, the query executor processes each frame in turn according to the SQL query and then generates result frames. At the same time, according to the distribution of objects in the frames, the system will trigger a continuous reoptimization mechanism to change the structure of the query execution and thus maintain a high processing rate. The query execution module utilizes popular deep learning frameworks to execute the query. We introduce progressive filters, which instantiate different operators for each object in the query. Each operator components consist of a sequence of deep networks of increased complexity, that is, the number of deep neural layers. For example, as shown in this picture, we use operator 1 to filter out the frames that don't contain object 1. Operator 1 consists of filters 1, 2, and 3, each being a deep network with an increasing number of neural layers. The larger the depth, the more the accuracy of the operator. Frames that pass the previous filters are checked by the subsequent filters and then routed to the front end for display. For a particular object type, progressive filters use the selectivity of the filters to derive the optimal filter sequence. The filters should be applied to minimize the total cost of processing the video stream. Taking the example of operator 1 as well, during an execution instance when object 1 is detected on the current video stream, only filters 1 and 3 can be applied to achieve the optimal result without filter 2. Since one cannot expect the distribution of objects on video frames over time to remain the same, we propose an algorithm to assess incrementally when the statistical properties of the underlying object distribution change. When such properties change, we trigger reoptimization, deriving a new optimal filter sequence to deploy until the next reoptimization. The basic idea behind our proposal is to treat the selectivity of filters as a statistical population. In that way, we employ a change point test and monitor the underlying distribution of objects relevant to the query between two epochs and trigger reoptimization when the statistical properties change. Such a strategy can improve accuracy while maintaining a high frame processing rate. In order to address our ultimate objective, each frame that contains the specified objects has to be processed by a deep learning model that determines the type of interaction between objects. Interaction sheaf is a filtering mechanism for object interaction queries. The basic observation is that the interaction, such as human hitting a tennis ball, typically takes place at a specific spatial region of the frame involving the first object, that is, the human. For each type of interaction, we could propose a model to identify such regions. Only when the second object is located within a spatial region relative to the first object, the frame is relayed to an expensive object interaction model for further processing. Thus, by processing the objects spatially, we obtain a filtering mechanism for interaction. The interaction sheaf module inspects the spatial location of objects on frames and filters out frames that, although contain objects relevant to the query, they are not promising to encompass the suitable interaction among the query objects. Our final proposal combines these three techniques, delivering an effective framework to process object interaction queries, efficiently improving the frame processing rate in a video stream dramatically. We now describe how the user interface of the system looks like and its associated functionality before we present the demo. The main wireframe of the SVQ interface is on the screen. SQL queries are defined through query definition, which is shown in the left sidebar, that is area, and enhanced with UDFs to manipulate video object primitives. The generated SQL queries, which are shown on the upper left center, are dispatched to the back-end, which is responsible for parsing the query. The progressive filters ordering per batch is presented on the upper right architecture module. It will be updated at the end of each batch. This order is determined by the online optimization algorithm based on the filter selectivity. The red box and nodes represent human operators, and the yellow and blue ones represent the object operator and interaction sheaf respectively. The lines indicate which filters are used. The yellow and blue ones represent the object operator and interaction sheaf respectively. The lines indicate which filters are used. By clicking the optimization button, our approach will be invoked, while by clicking the brute force button, state-of-the-art object detectors and action recognition models will evaluate the respective input video. We can observe the query results and the performance of our proposed algorithms under the optimization area. We visualize the query as a red heat map appearing on the frames. The bounding box of the human and baseball are also displayed. As we can see, multiple data sets containing different interactions between humans and objects are available to choose from. Here we choose the baseball dataset as the first example, which contains interactions between a human and a baseball. The system supports both slow and normal mode to visualize the results. In slow mode, the results are displayed in a few frames per second to inspect clearly the outcome. We'll choose the normal mode here. We choose the interaction predicates and check the only available option of the particular interaction, which is human throwing baseball. Next, there is the SQL query processor. Users can execute their queries involving proper UDFs that can process the frames. As we can see, after choosing the particular set of the dataset and predicates, the query is generated. After pressing the interaction sheaf button, the video is processed. We can observe that the order of the operators is different across batches of frames. The lines indicate which filters are used, and the thick lines display changes from the previous order. After the query execution, we observe the statistics including the F1 score, the true positive and negative rate, and the precision in the accuracy area. We can also observe the processing time overall and the average frames per second for different operators in the performance module. In the second row, we can compare the full model. Here we run the full model, which processes the same video without the use of filters, and each frame is processed on fast RCNN, resulting in a slow processing rate. Similarly, the interaction predictions are displayed as the red heat map. We can also see the statistics for the full model and in particular the F1 score and total processing time. It can be seen that in the performance of F1 score, precision, and true positive rate, our proposal lags behind the brute force model, but it is the opposite of the false positive rate. The optimization mode can deliver up to 2 orders of magnitude performance advantage. The total time of the optimization mode is 5.5 seconds, and it is 30 seconds for the brute force mode. We use 3 colors to represent the time spent by each operator respectively. We have considered the problem of efficiently executing queries on video streams involving certain types of interactions between object types detected in video frames. We presented a system for streaming video queries involving interactions. Our system can achieve significant performance advantages with a very small loss in F1 accuracy. This work opens numerous avenues for further study. Declarative query languages and query processors for video streams is largely an open research area. Thanks for watching.